Here is the partial flow diagram in cross-section. A circular sewer pipe of diameter d, but sewage flows at a depth d which is less than d. There is always an air space above the water. This is not by accident, it is by design. Why do we never design a sewer to run full? 5 reasons. 1. Ventilation. Sewer gases like methane and hydrogen sulfide must escape upward through that airspace. 2. Peak factor. The peak flow can be 2.5 to 3 times the average. A pipe sized to just full at average flow will surcharge every morning and evening. 3. Future allowance. Population grows, infiltration enters, illegal stormwater sneaks in. 4. Surcharge prevention. A full pipe under extra flow creates back pressure, manhole overflow and basement flooding. And 5. This is the subtle one. Velocity becomes maximum before the pipe is full. Look at the curves. At depth ratio 0.81, velocity hits its peak at 1.14 times the full pipe velocity. At 0.94, discharge hits its peak at 1.07 times. So running a sewer not quite full actually gives you more capacity than running it full. So for sanitary sewers, we designed for a depth ratio between half D and 0.8 D. Storm drains are checked differently, often for full or surcharged conditions. In our last video, we saw that the partial flow chart has 2 peaks. Velocity peaking at d over d equal to 0.81 and discharge peaking at 0.94. But why today we will derive every curve from first principles, so by the end you will understand exactly what is happening. First, the setup, a circular sewer of diameter d with water flowing at depth d. The wetted portion subtends an angle theta at the center. Our master relationship is d divided by d equals 1 minus cosine theta by 2, all divided by 2. When theta is 180 degrees, the pipe is half full. When theta is 360 degrees, the pipe is full. Now, the first ratio area. The wetted area divided by the full area A equals theta minus sine theta all over 2 pi. The curve starts at 0, reaches exactly 0.5 at half full, and reaches 1 when the pipe is full. Next, wetted perimeter, P divided by P is simply theta divided by 2 pi. A perfectly straight line at half full, it is exactly half, at full it is exactly 1. Now, here is the first big surprise, the hydraulic radius R over R equals area divided by perimeter, which simplifies to 1 minus sine theta over theta. Look at this curve carefully. At d over d equal to 0.5, half full R over R is exactly 1, the same as a completely full pipe. A half full pipe has the same hydraulic radius as a full pipe. This is an examiner's favorite, remember it. Next, velocity comes from Manning's equation. V varies as r to the power 2/3, so V over V equals r over r raised to the 2/3. This curve peaks at d over d equal to 0.81, with V over V equal to 1.14. The pipe runs faster than full pipe velocity in the range 0.5 to 0.94. And finally, discharge. Q equals velocity times area. So Q over Q equals area ratio times velocity ratio. This peaks at d over d equal to 0.94, with Q over Q equal to 1.07. But why these specific peaks? Here is the intuition. As d over d goes past 0.81, the wetted perimeter grows faster than the area, so R drops and V drops, but the area is still growing, so discharge keeps rising until 0.94, when even the growing area cannot beat the dropping velocity. For your exam, lock these numbers in. At d over d equal to 0.5, R over R is 1, V over V is 1, Q over Q is 0.5. At 0.81, V over V is 1.14. At 0.94, Q over Q is 1.07. And this is exactly why we design sewers between 0.5D and 0.8D. You stay below the velocity peak, you have headroom for peak flow, and you preserve self-cleansing velocity. You have seen the partial flow geometry in 2-dimensional cross-section. Now let me show you what it actually looks like in 3 dimensions. Here is a circular sewer pipe shown as a transparent cylinder so you can see inside. Now I add water. It fills the bottom portion of the pipe to a depth d with a flat free water surface on top. The shaded region you see inside is the wetted volume. Its cross-section area divided by the full area is exactly the ratio we plotted in the last video. Let me rotate the view so you see this from different angles. From the end, you see the same cross-section we drew in 2D, the chord, the depth d, and the central angle theta. From the side, you see the flow moving along the length of the pipe, and from above, you see the rectangular free water surface, the ventilation gap that lets sewer gases escape upward into the atmosphere. Now watch what happens as d over d changes. Starting from half full, the water rises slowly. At d over d equal to 0.81, this is where velocity hits its maximum. The hydraulic radius peaks here at 0.94, discharge hits its maximum. And at full, see how the free water surface disappears completely. No air gap, no ventilation surcharge risk. This is exactly why we design sanitary sewers in the depth band d over d between 0.5 and 0.8. The water carries the flow efficiently. The air gap stays open for ventilation, and you have room for peak flow and future growth. The three-dimensional view makes it clear every depth ratio is a real physical state of the pipe, not just a number on a chart.